Hi, Skillets. Okay, today we're going to do the 3.1b lesson. The 3.1b lesson is all about logistic growth. And probably that sounds a little bit familiar because when we were learning the 12 basic functions, one of them was the logistic function. And the logistic function looked like this. And it had an asymptote right there, and it had an asymptote right there. Logistic growth is what exponential growth looks like in the real world. So if we have a population that just keeps growing exponentially, that's fine for a while. But eventually, wherever that population is growing will run out of space or resources or both. So like right now, the population of Earth is growing exponentially, but eventually we will run out of space on this planet. We will run out of resources in order to sustain life on this planet. So right now the growth is exponential, but far in the future it will start to taper off because the planet can only hold so much. And so that's what happens with logistic growth. It grows really fast for a while, and then it starts to taper off. So there's a limit to the growth, and it's at that top asymptote. So you're going to see two different versions of the logistic equation, but let's write down what I just talked about. So a logistic function, it grows exponentially for a while, and that while is different depending on each scenario, but there's a limit to growth. And that limit to growth, go ahead and just remind yourself that it's a horizontal asymptote. So here are the two forms that you could see for for logistic growth. One of them is f of x equals c over 1 plus a times e to the negative kx power. They're not little functions. And the other one, or you could see it this way, f of x equals c over 1 plus a times b to the x power. So some of them just use any old base, b, and some of them specifically use the base e. This one is the one that we'll see more often with the base of e. It's the one that we're going to make our calculators use. You're going to see it more because, again, Euler's number e occurs really often in real life. This is the one that you had to memorize for the 12 basic functions, except it was the basic one, so everything was as simple as possible. So the c was 1, the a was 1, and the k were 1. So it looked like this. The c was 1, the a was 1, the k was 1. This is the one that you memorized for the 12 basic function sheet. All right, so that c is the most important number for us because it's the one that we're going to look at the equation and we're going to automatically use that c. The c is the limit to growth. The c is the maximum sustainable population. It is the maximum number of whatever you're counting that can be in that space. So it's the maximum number of people, it's the maximum number of bacteria, it's the maximum number of deer, whatever the situation is, it's the maximum number that can be held in whatever that space is. And for that reason, it's also the horizontal asymptote. Now notice that the logistic function has two horizontal asymptotes. One of them is always y equals 0. So sometimes with your logistic function, you could have a really high top horizontal asymptote because you're talking about like the population of Earth or like the population of bacteria can be a huge number. Sometimes, like if you're talking about the population of a classroom, the number will be a lot littler, you know, like maybe it's 30 or 15 or whatever the case may be. It totally depends on the scenario. So you're going to look at the logistic function and right away you're going to be like, ooh, I know that top number. I know the top horizontal asymptote. That is the maximum sustainable population. It is the limit to growth. No growth can go beyond that point. Right? Now, also remember that in this class, we round to 3 decimal places, except when we're talking about like things where it doesn't make sense to round to 3 decimal places. So for instance, number of people, number of bunnies, we often have to round to the nearest. So if you have a horizontal asymptote of 70, you might be like, oh, well, that means that it can't equal 70. Oh, but it can, because you can have 69.9 of it, and then that would round up to 70 because we wouldn't say that you can only have 69.9 people. That would be a real bummer. So we are often rounding, and that's why our maximum population can end up being what the horizontal asymptote is. It's a limit, so it will look like it equals that number. Okay, so let's do some examples. Example 1. Graph and find Hassies and y-intercept. Problem A. F of x equals 2 over 1 plus 2 times 1/2 to the x power. So you're just going to graph that in your calculator. But when you graph it in, make sure that you're putting this entire denominator in parentheses so that your calculator knows that's the whole denominator. So I typed it in like that, and I'm going to hit graph. And I can see it have that shape, right? I can see there's the horizontal asymptote right there, and then it grew for a while, and then it's leveling off again. So I always sketch what is shown on my calculator on my paper. So it looks like I've got, all right, so I've got this horizontal asymptote and this one. The bottom one's always y equals 0. And then the other one, I can kind of see what it is on my calculator, but I know what it is because this right here is C. It's the limit to growth. So that top Hassie is y equals 2. Those are the horizontal asymptotes. Now let's find the y-intercept. There are 2 different ways to find the y-intercept. One of them is just to make your calculator do it, right? You can either like, the easiest way is to look at the table, second table, and then when x is 0, what is y? So I can see that it's 2/3, right? The y-intercept is 0, 2/3. But I can also just plug it in myself without needing to make my calculator do it, because when you're plugging in 0, you're plugging it in the exponent spot, and an exponent of 0 is nice and simple. So 1 plus 2 times 1/2 to the 0 power. So 1/2 to the 0 power is just 1. So now I just have 2 over 1 plus 2, which is just 2 over 3. Right? So that's another way to find the y-intercept, is just to find what f of 0 is. All right, let's try B. F of x equals 15 over 1 plus 3 times e to the negative 2x power. Okay, I'm going to plug this in. I see that 15 on top, right? So I already know where the top horizontal asymptote is. Actually, I know both of my asymptotes. So just as a reminder, when I'm typing this in, I've got this e to the x button right here, which will not only put the e, but it will also make it be an exponent for me. So that's really handy. And then I need to use a negative 2x up there. Close the parentheses. graph. Now, right now on my screen, I don't see high enough to see it level off because I only see up to 10. I know that this is going to go all the way up to 15. So I need to adjust my window. So I'm going to hit the window button, and I need to make my Y max be a little bit bigger. I'm just going to go a little bit bigger than 15 so I can see just a little bit more than I need to. So see, right here in this time, it grew really fast. Shot up, and then it was like, ooh, we're out of space. So I see it cross and then shoot up and then level off. All right, so y equals 0 and y equals 15. And then to get my y-intercept, I'm just going to go ahead and plug in 0. F of 0 is 15 over 1 plus 3 times e to the 0 power, right? Negative 2 times 0. So blammo, that's 1. I have 15 over 1 plus 3, 15 over 4. So that's my y-intercept. 0, 15 fourths. If you want to write that as a decimal, you can, because it's a fourth, so it's going to work out really nicely. It's just not important. So this is often used with population modeling, again, because we'll run out of space. So sometimes when you're doing population problems, they'll have you do it exponentially because, you know, it's at the beginning of the population growth and it's still showing exponentially. Sometimes they'll have you do it in terms of logistic growth because the place is running out of space. So for instance, they might be like, Dallas is constrained by the cities around it. So not many new homes can be built. So now the population is growing logistically. So they'll give you a little scenario where it makes sense to be logistic instead of exponential growth. Okay, so here is example 2. Actually, this one is about Dallas. Maybe that's why I came up with that. All right, Dallas is constrained by neighboring cities, and its population can be modeled by y equals 1,301,642 over 1 plus 21.602 e to the negative 0.05054 t power, where t is years after 1900. When was the population 1 million? So if you need to pause in order to write that equation down or whatever, that's totally fine. All right, I'm going to type this equation into my calculator. So when I typed it in, obviously I couldn't use a t, so I used x. And make sure that you put the negative because this will be a totally different equation if it's not a negative exponent up here. Okay, now before I graph it, I know that the window I have is not going to work out because the top asymptote is at 1.3 million. So I knew that I need to see higher than the 16 that I have right now. So I'm going to go ahead and change this to 1,500,000 because then I know that I'll be able to see enough. So I'm going to see it grow. I don't see enough of the growth, and probably that's because I'm only seeing 10 years right here. So I'm going to go ahead and adjust a little bit so I see more than 10 years. Maybe I want like, I don't know, 150 years. Let's see how fast it grows. There we go. And so I saw it grow, and then now it's leveling off. So this was 150 years after 1900. So this brought me pretty far in the timeline. I'm going to go ahead and graph this because I'm going to use my calculator to solve this equation. So I see it go, and I know that this up here is that like 1.3 million. Y equals 1,301,642. Okay, but I want to know when it's a million, exactly a million. Okay, so what I'm going to do on my y equals, I already have the equation, and now I'm going to type in just straight up 1 million. And that's going to graph a flat line at 1 million. I want to know right there where they touch. So this is the line y equals 1 million. I want to know right there. I'm going to make my calculator tell me when that is. So on your calculator, you're going to use right there where it says calc. So second calc, and I want to know where these two things intersect. It's been a while since we've done that. So when it says first curve, you're going to hit enter. And when it says second curve, you're going to hit enter. And when it says guess, you're just going to kind of move it to where they touch. Now this is easier on Desmos because on Desmos, you can just touch the place where they intersect and it'll tell you what x equals. So this is telling me that x equals 84.513. Okay, so it took 84.5 years to get to 1 million. So they want to know when, like, when did it reach 1 million? So I'm not going to say 84.5 because that doesn't make any sense. I need to add that to 1900. So I'm going to say in 1984. And if you want to be like, well, it's halfway through 1984, it's like June 1984, then okay. But I just need you to give the year because that's what makes sense in this scenario. All right, so now last thing is that we can also do logistic regression. Okay, so this table models Pennsylvania's population. Okay, and I gave you years and then how many millions of people. And I don't need you to change this to a bunch of zeros. You can just leave it in this way because the numbers are way smaller. Okay, so with this, I would like you to please do a logistic regression. So problem A, find the logistic regression equation for Pennsylvania's population. So that means we're going to type this into the calculator. Okay, and as a reminder, you can type it in like in the graphing calculator. You can type it here by hitting the stat button. So if you hit stat and then edit, and then you can type it in there and see that I've already typed it in here. Or if you prefer, you can also type it in Desmos. So I'm just going to show you that really fast. Not quite that tab, but this tab. There we go. Okay, so I typed in the table right here, and then I needed it to do a logistic regression equation. So on Desmos, remember you do that, those of you that are using Desmos to do a regression, this is what the equation looks like for a logistic regression. So if you're using Desmos, you're going to want to write that down. And then those of you that are using your graphing calculator, like a physical graphing calculator, I'm going to show you here where we select that on the graphing calculator. Okay, so on here, you're going to hit stat, and we're going to go over to calc because we're going to do a regression. And you got all these options. You want the one that says logistic, which just straight up says the word logistic. And the calculator has to think pretty hard about logistic regression, so if it takes a little bit, that's fine. I would like to point out, I think that I forgot to say it, I didn't use 1900, 1910, 1920, because we like never use years. I used years since 1900. So that's why I entered 0, 10, 20, 30, 40. Okay, so I'm going to write out this equation and see it gives me like what the shape is supposed to look like, and I'm just going to fill in stuff. And remember, we round to 3 decimal places. So when I write this out, y equals, and I know that c goes up on top, right? So 11.923, and then 1 plus a, which is 0.855, times e to the negative, they called it b here, 0.0, and I'm gonna have to make that 40, and then x. That is my logistic regression equation. Okay, so then part B says, find the maximum sustainable population of Pennsylvania. Remember, maximum sustainable population, that is the most people that could legitimately live in this case, Pennsylvania. It is the same thing as the horizontal asymptote at the top of the graph. It's also the same thing as C. So when I ask you for the maximum sustainable population, or I ask you for the limit to growth, every time I'm asking you the same thing, I'm asking you for C. So you're just going to answer, you're going to look up there and be like, oh, hey, there it is. I'm going to say 11.923 million people. So I left it as 3 decimal places because it's in millions of people, not just people. That's not 12 people right there. It's not quite 12 million people, right? Blammo. All right, hopefully that went well for you. Go ahead and take the 3.1B quiz.